Welcome to the global meeting for our outdoor monitor testing. You might remember, at least some of you, that we had a meeting in April. And since then, I think a lot of evolvement and new partners came on board. And what we want to present today, especially Annika, is like the first results of our analysis and some discussions on these and how we want to continue. Before that, I would like to give a quick introduction, and some of you might have seen. So just recently, we gave actually ourselves as AirGradient a manifesto, and that gives actually a really good overview about like how we want to be as a company and what probably distinguishes us from many other players out there. So we have that on our website, and that's just like the short version. And I just want to highlight a few things here. And one is probably the second point here, which is very applicable for today. So we really believe in open science and with this open source, open hardware mindset. So all the algorithms that we develop, the data we want to really share with the community, so that like hopefully we can have an impact on air quality monitoring worldwide, on better understanding these monitors. We work a lot with NGOs, so some of them are also on the call here, and that's also like the main purpose of really the co-location here, to develop a really good understanding on the performance of the monitor as well as the limitations, so that communities, if they want to use the monitor in their communities, that they know how to use them and what they can do with the data. So we have a lot of partners in the meantime in the consortium. We cannot do like last time an introduction, because then probably the whole round would be over already. But what we are thinking about is actually to plan to have an air quality forum, potentially in December, to give a platform for all the partners here to present parts of their research. So if you're interested in participating, then you can drop us an email. We will also actually send out a form and ask if people are interested on participating and what kind of topics they would potentially like to present. And then we will also ask in that form if you want to share your contact details with the group, and then we will send these contacts around with the people who want to share their contacts. That's all from my side. So I would like to hand over to Annika.
Thanks, Achim. Yeah, I will actually continue with the same presentation, but it's better when I have the power of the clicking. Yeah, as Achim already mentioned, today's main focus is on the co-location tests. And most of you will already know what that means, but we might also have some newcomers, so I'm just going to summarize it in a few sentences. It is about testing the performance of this AirGradient outdoor monitor, the open air. And on the map here, you can see the locations where our partners, our collaborators are, and they support us by kindly providing a reference instrument. And we have sent, or are about to send, because there are also some new locations which we're just setting up, for example, here and in Australia. Usually 2 or 3 monitors, and co-locate them with a reference instrument. And the reference instrument measures particulate matter, or generally air quality, as an official standard. So it's kind of recognized standard instruments, which are kind of the golden aim, which we are aiming to measure. So by comparing the reference with the monitors, we can find out how good the performance of the monitors is. I have just a few additional words to CO2 sensors before I get into the data analysis. So we got a few requests from people about CO2 monitoring for the outdoor sensors. And these CO2 monitors have kind of interesting applications, for example, climate studies, or CO2 could also be a proxy for combustion emissions such as traffic. And so we picked up on that, and we are already working on a prototype, or we have already created a prototype where instead of having two PM 2.5 or PM modules in the outdoor monitor, we have replaced one module with a CO2 sensor. And the prototypes have already been sent to Cambridge and Birmingham, where they're already being tested, and the first results look pretty promising. So if you also have a CO2 reference instrument and you would like to join this testing, please let us know, and then we can also just send you a prototype, and you can see, yeah, we can see how well the performance is, and also you can see if you might like it. Okay, but now to the data analysis. As Achim already said, we have a great consortium with lots of strengths, and also we have lots of perspectives within our group on how to look at air pollution. So we have scientists which look maybe at very technical aspects and measurement aspects. We have NGOs, we have governmental organizations. So in the following data analysis, I'm trying to keep a balance between being not too scientific that no one can understand it anymore, and also not too, you know, too superficial. I hope I'm not going to bore anyone, or I'm not going to confuse anyone. But if you have any questions, please just shout. I can't see you right now, so just make some noise and just ask your question. The performance analysis, so that's our goal, right, to figure out the performance of the monitors, is based on the guidelines from the Environmental Protection Agency of the United States. I will also circulate this presentation later, so if you're interested in that, you can follow the link in this presentation. It's quite a comprehensive overview on, or guideline on how to test the performance of low-cost sensors. And one thing they talk about is data completeness. So if you aggregate data, so if you want to have a different time resolution, for example, you want to aggregate it from 1 minute to 5 minutes, or from 5 minutes to 1 hour, we have to do that sometimes with the AirGradient data, so to adapt it to the time resolution of our reference data. Then you need to make sure that within these windows you're aggregating, you have enough data coverage, so at least 75%. So that is one thing we implemented, that on both sides, in reference data and in AirGradient data, when we average it, that we have at least 4 or 5 data points when we average it to 5 minutes, and equally 9 of 12 data points when we average it to 1 hour. Also mentioned in these EPA guidelines is data cleaning. Currently, we spot outliers via histograms. So here on the right side, you can see a histogram. That means on the x-axis, basically, you can see the values of measurements. So here the temperature measured in Cambridge at a reference instrument over a couple of months. So the temperature goes between around 0 degrees to something like 35 degrees. And you can see that there's one measurement which is at -50 degrees. So this is also not connected to the rest of the measurements, and therefore quite obviously an outlier, also because it's very rare that you have -50 degrees. So this is currently the way how we spot outliers. Also, if you have physically impossible data, such as a negative relative humidity value or so. However, that is very rare in both the AirGradient data and in the reference data. So, but yeah, so this is one step we have been doing so far, only for the reference data. So if you, like in the following analysis, where I compare the reference data and the AirGradient data, I used cleaned reference data and raw AirGradient data. So potentially the raw AirGradient data could even improve a little bit once we did the cleaning. But as I said, there is not many outliers. the first thing we looked at is the reproducibility of only the AirGradient sensors. So that means if you put multiple AirGradient sensors close to each other, so they measure the same air mass, they should measure all the same. And here I've picked an example data set from Cambridge. We have there 3 monitors, which each include 2 sensors. So in total, we have 6 PM sensors. And here in this graph, you can see a timeline of the PM 2.5 concentration measured over 2 months from 6 monitors. And as you can see, all the lines overlay, so you can actually not even make out 6 different colors. So already by just looking at it, you can see that the agreement between the AirGradient sensors is pretty high. But you can also quantify it a bit more. And for this, you can use scatter plots. So here I have plotted 2 of these sensors against each other. And you can see that there's a clear linear relationship. And the closer these points are to the one-to-one line, so this black line here in the middle, the better the sensor agreement. And there is also a parameter that describes the linear relationship between 2 parameters. This is the coefficient of determination, R², and the closer this is to 1, the better the agreement. So in this case, we have an R² of 0.97, which means that's a pretty good agreement. But in this case, we've only just compared 2 sensors. So if we want to compare all sensors in Cambridge, we can use a correlation plot. So here you can just look at the 6 sensors again and compare, for example, sensor 2 with sensor 4 would have an R² of 0.96. And as you can see, they all have really high R² values close to the value of 1, which means that we can conclude that there's generally a high correlation between the sensors. They agree with each other and hence they're reproducible. As a next step, I want to look at the difference in locations. So I have done this analysis in all locations. So to compare that, I create just one value, kind of simplify this, just take the average R² value, excluding the ones, of course. This would be for Cambridge, this would be 0.994, so really close to 1. And here we can see a table of different locations. So Cambridge is here, but there's also Thailand, London, South Africa, which is close to Johannesburg, and Canada. And you can see that they're very different environmental conditions. So we have different temperatures, we have different RH, relative humidity ranges, and we will most likely also have quite different compositions of particulate matter. So quite different environmental conditions, and you can here always see the mean R² value for each location, and all of them are still above 0.9, so very close to 1, which means as a general conclusion, we can say that we don't need to worry about the reproducibility of the AirGradient monitors. They all measure the same, basically. But as a next step, we also want to compare the AirGradient monitors not only with each other, but also with the reference instruments. That's why we distributed them over the entire planet, basically. So here we have the same example data set, but now comparing the one AirGradient monitor here in black with the reference measurements of PM 2.5 in red. And here you can see already by eye that there is a bit more of a difference. For example, in this peak here on June 10th, it's about 10 micrograms per cubic meter. And you can just, like, the easiest way to look at these differences is to just subtract one parameter with the other. So we have here the differences plotted again in a histogram for this time period. And as you can see, most of the data differences are around 0, so that's good. And this can also be summarized with a root mean square error. This is kind of the average difference between sensor and reference, or 2 parameters in general. So here we could say that on average difference between the sensors and the reference is about 4 micrograms per cubic meter. And another way to also look at the performance of the sensors is, as you already have seen, these scatter plots. Here again, we have the R² value, 0.81, which is lower than between, like, it's within the sensors themselves, but it's still fairly close to 1. And now you can see that these points still show a linear relationship, so they're still on kind of a line. However, this line is not on this one-to-one line anymore. And this is some kind of systematic disagreement between the sensor and the reference. And this you can look at with a linear regression. So we kind of fit here a line between these points. And from that, we get a scaling factor. So basically, how much you would need to scale this to get from the one-to-one line to here. And also an intercept, which is kind of the intercept here at the y-axis. And since it is a systematic disagreement, this can be corrected for via a calibration. So here I show you how this calibration is done. I pick a part of our data set, in this case the first month, as a training period. So this is the period where I extract the calibration parameters from. And I use these data to do the linear fit, which I just shown, and I extract the scaling factor and the intercept. And then I apply it to the entire data set. And as you can see, the data already visually agree much better now with the reference data. And also not only during the training set, but it kind of, the calibration then also works for data sets which were not included in the calibration. So if we compare now the raw data, which comes straight out of the instrument, and the calibrated data, you can see that the difference between the monitors and the sensors is decreased significantly, so it's more than half now. And also that the scaling factor is much closer to 1 now, which is good. Ideally, you would have a scaling factor of 1. And also that the intercept became smaller. So this is all good news. And as a next step, I would like to get these are the performance parameters, basically, of the sensors, which are also the parameters which the Environmental Protection Agency suggests to look at. And I would like to collect these from all the different locations. For this, we still need to gather the reference and also manage the reference data so that it's all formatted and so on. But yeah, this is the next step. And then I'm really interested in how these calibration parameters differ across locations. And can we extract from this information, can we somehow extract a global calibration procedure? So in an ideal world, we wouldn't need a reference instrument anymore to calibrate this. So that will be the next step. And another step I would like to do is to look at the effect of relative humidity on the particulate matter measurements. So here you can see a graph where this is a calibrated data. It's exactly what I've shown you before, but now it is colored by relative humidity. And you can see that if the relative humidity value or RH value is low, then you kind of have a different line through your data than when you have a high relative humidity. So if you have high, then the data is more below the one-to-one line, and if you have low data, then the data is more above the one-to-one line after this simple calibration I have just performed. And so you can, so this is the raw data, sorry, this is calibrated, this is raw, but doesn't really make a difference. You can see that there are kind of different scaling factors or slopes or gradients in these lines. And to compensate for that, I have thought of a method which I haven't heard before, so it's not very common as far as I know. So I would like to hear your feedback on that. So as you can see, it has different scaling factors. So I thought about doing the same calibration method with a training period, but now do it specific to the relative humidity. So here you can see a timeline, again, the same data, but now I have plotted the relative humidity. Again, I use the training period to calibrate my data set, and now I split the set by relative humidity. So I get, in this case, I split every 10%, but this is quite random, that could be optimized. And I extract from each of these kind of relative humidity bins, I extract again the scaling factor and the intercept. And then I apply it to the entire data set again by relative humidity bins. And this is the result. First, looking by eye, you can't really see much difference between the normally calibrated data and the RH-specific calibrated data. But if you zoom in a little bit more, then you can see, for example, here that the data actually aligns a little bit better. So it means the agreement between reference and AirGradient data is better. And if we look at the scatter plots again, and also on our parameters here, our performance parameters, we can see clearly, or a bit better, that the performance is has enhanced again. So we have a bigger, like an R squared, which is closer to 1 again. The RMSE, so the kind of average difference between a reference and monitors, has decreased. The scaling factor is closer to 1. Yeah. So here you can see kind of an overview of all of these 3 steps, which of AirGradient data. And now I already want to come to my summary. So as I said, you did a performance analysis based on EPA guidelines. So far, we looked mainly at the data from Cambridge. We found that there is a very high reproducibility among the sensors, so the sensors agree very well with each other. There's also high linearity between the reference measurements and the AirGradient sensor measurements. So in Cambridge, that was an R squared of 0.81. Overall difference can be improved by calibrating the sensors, and it can be further improved by doing a relative humidity specific calibration. And that's actually already all from my side. I'm happy to hear your comments and ideas or questions, especially to the RH correction. I would be curious what you think about that.